Okay, I think we can get started. Welcome, everybody. So it's a pleasure to welcome our speaker today. It's Murray Elder from University of Technology, Sydney, and he is going to tell us something about groups presented by inverse closed finite convergent length reducing rewriting systems. All right, please.
Thanks, Ilya, for my very long title. Thanks, everyone, for coming. It's a great honor and pleasure to give the New York Group Theory Seminar talk. So I'm going to tell you what all these words mean. And this is joint work, various parts, with my student, John Koo, Heiko Dietrich, and Yuming Chow, both in Australia, both finite group theorists. Adam Piggott at ANU and Armin Weiss, Stuttgart. So I'll show you what contribution everyone made. The plan is to talk about the isomorphism problem, which needs no introduction for this crowd. I'll tell you what a plane group is. Doesn't sound that exciting, maybe, the name. Rewriting systems. And then I'll give some of the new work that Adam and I have come up with, geometric characterization of these groups and an algebraic characterization, and then I'll give some complexity results. So please interrupt at any time. I haven't turned on my chat, but that's only for students, right? You guys will yell out. Okay, so recall that the problems on input to finite presentations are the groups they present isomorphic. And on input, I think Chuck Miller taught me this many years ago. On input, a finite presentation, does it present the trivial group? And these problems are famously undecidable. Novikov and then Adian Rabin for the last one. So that's well known. However, if we're given two presentations and a promise that they're in some class, virtually free, hyperbolic, other things, then it's possible that, and indeed turns out in those two cases, that the isomorphism problem is decidable. So here's some history. So Krishtik, virtually free groups given by presentations is decidable. Awesome. So this is an ingredient in the hyperbolic. Rips and Seller, canonical representatives for torsion-free hyperbolic groups, was a method to reduce equations over hyperbolic groups to equations over free groups. And so that's an ingredient in Seller's isomorphism for torsion-free hyperbolic groups. Given a presentation is all you need. You set up, you can decide isomorphism. And so quite a while later, so 2010-11, Dharmani Giridhar extended the idea of canonical representatives to all hyperbolic groups, and so they could solve equations in any hyperbolic group by reducing equations to equations over virtually free groups. They showed how to solve equations in virtually free groups as well. And putting all that together with some JSJ stuff, you can decide isomorphism for all hyperbolic groups. There's an algorithm. Okay, so now we know that things are decidable. The obvious question to many of us is, what is the complexity of those problems? So I want to show you that we can't have any complexity. So that's the purpose of this slide. So just with a promise, the groups lie in some class, and so you're just given two presentations and a promise that they're both, say, hyperbolic. Let's see what happens. Suppose isomorphism was decidable in 2 to the 2 to the 2 something space. Suppose you had some great algorithm to do that. So then we could input an arbitrary presentation together with your favorite presentation for the trivial group and run this alleged algorithm on the two presentations. If the algorithm terminates within this space bound, it'll say, no, one group is hyperbolic but not trivial. And so you'll know that the group was not trivial. Or it might say yes, and your group is actually trivial because the trivial group is hyperbolic. And if it doesn't terminate in that space, well, it's supposed to give the right answer on this class of hyperbolic groups. So therefore you've deduced that your group is not hyperbolic. So in particular, it's not trivial. So that's what it says there. So that would contradict Adi and Rabin that we'd have some algorithm to decide triviality of a presentation. So Darmani and Girardel say quite clearly in their work that there's no mention of complexity in this work, that we're giving a decidability algorithm. And there's no way you could have any complexity just given two presentations and a promise. But if we really want to get complexity results, we need more than just presentations and a promise. So Senegers and Weiss studied virtually free groups. And this is two things that they proved. So if you have two virtually free groups specified by something more than a presentation. So the first one is a context-free grammar that generates the word problem. And of course, we all know that a group is virtually free if and only if it has a context-free word problem, collection of all words equal to the identity. So that's a perfectly legitimate, maybe natural, one might say. I can't see people frowning when I say that. Natural way to be handed a virtually free group. And so if that's the input, they can actually get a complexity result because there's no contradictions lurking around with decidability. And their result is that this can be done in doubly exponential space. The second result is that if two virtually free...
just a second. Yeah. So the word problem itself, does it, just a moment. So it,
yeah, you can get a presentation from...
So it does specify the group. So it's on a particular set of generators. So it specifies the group, right?
Yeah, exactly. So I guess you're given the terminal letters, the generators, and then the word problem will be all the relations where you can extract. Okay. Yeah, perfect. Yeah, and the second one, it's the name might be a bit off-putting. Virtually free presentation actually means quite a lot of data. It's not just a presentation. It's very tiny writing down here that a virtually free presentation is a technical thing. It's a free subgroup, you know, a free basis for a free subgroup you're given, and you're given a set of coset representatives, finite set of coset representatives, and then you're told all the different ways to multiply a generator of the free group and a coset representative and two coset representatives. So you're basically told how to do everything and put everything into normal form. So it's a bit sneaky to call it a virtually free presentation maybe, because it's quite a lot of data, but that also is enough to specify a virtually free group. And so with that, I haven't really explained it that well, but you can have a look at their work to get the precise definition. With this input, it's a piece-based algorithm to solve. So these are really interesting, I think, results for many reasons. And it kind of opens the door to, in a particular class of groups, when I have something more than a presentation, what's the complex, you know, is it possible to get a complexity? So that's what I'm going to come to at the end of the talk. And I'm going to give a complexity result about plane groups, which is a subclass of virtually free groups. So the result we have is that if we have two plane groups given in a certain way, so obviously not just as a presentation, and so something maybe inspired by the Senegers-Weiss result, we might try and have a formal language, or we might have some kind of technical thing. So we'll see what we claim is a natural way to present a plane group. Then the isomorphism problem is in a complexity class below P space. And I'll tell you what that is. It's somewhere in the polynomial hierarchy. Okay, so that's my introduction. Let's start with a plane group now. A plane group is something that's isomorphic to a free product of finitely many factors, each of which is a finite group or an infinite cyclic group. Looks like that, where each of those is a finite group. So what's an example? PSL2Z, your Cayley graph is made of triangles and edges like that.
So that's a special case of a virtually free group, right?
Special case of virtually free group. Yes, very special. You might say very plain, boring one. But that's what we're going to work with. We think it should have a more exciting name, and then people might be more interested. So they're good examples of virtually free groups, I guess. All right. So Basset theory tells us that a group is plane if and only if it acts geometrically on a locally finite tree with, so graph of groups, with finite vertex stabilizers and trivial edge stabilizers. Whereas a virtually free group is the same thing, but it has finite vertex stabilizers and finite edge stabilizers. Or the graph of groups has just finite groups labeling all the vertices and edges. So that's the difference at the level of Basset theory. We use that in our proofs, but I won't be using it explicitly in the talk. So in particular, we can see from that plane groups are virtually free and hyperbolic. So we're in that world. Here's just a bit of an aside. I thought this crowd might find this interesting. The reduced word problem for a finitely generated group is the set of words which don't equal to the identity, which don't have a prefix equal to the identity. So it's the first time that you come around back to the identity. A language, so that's one thing. A language is simple if it's generated by a context-free grammar in Greibach normal form with these restrictions that if you've got two productions where you produce a terminal, then the suffix has to be identical. That's quite a restriction. And if you produce the empty word, then that's the only production in the grammar. So that's what a simple is never simple in mathematics for some reason. So that's a simple language. And here's the result of Haring-Smith from 83. A finitely generated group has a presentation with a simple reduced word problem if and only if the group is plane. So there's perhaps an obscure characterization of being plane. And so you might think from here that I might use this as the input to a isomorphism problem in analogy with Seneger's and Weiss context-free grammar, but actually we don't. So there's something that's a bit interesting. Okay, so I'll talk about rewriting systems. And this is going to be the input that we claim is natural to represent plane groups. So that's why I'm doing it. And our original motivation, Adam Piggott and I, was to try and solve a conjecture about rewriting systems, which I'll tell you. So a rewriting system is simply a pair of a non-empty set of letters and rewrite rules left, right. And the idea is that if you see a left side in a string, you'd just replace it by the right side of the string, and you can move around strings like that. So here would be an example, a very simple example of a rewriting system. If I ever see a little a next to a big A, I can replace that by the empty word. You might already be imagining what's going to happen there. So here's some notation. We write A goes to B. If you've got A with an L factor and B has the R factor where the L was. Okay, so in our example, we can replace that. We can replace that. We can replace that, and we'll be left. Oh, I need some more notation. So I did 3 moves there. So I put a star on top to say that just goes to A in 3 steps. So I don't have to write it all out. So the reflexive transitive closure of arrow is arrow star. You can have as many moves as you want. And the reflexive transitive symmetric closure is called equivalence. And I feel like I'm teaching my first year class just doing this bit. But that's what it is. And we go backwards and forwards with the star. So then we get equivalence classes of strings coming from this rewriting system. And the operation of concatenation on strings is well defined, the little exercise on these equivalence classes. And so therefore we get a monoid, a set of equivalence classes with concatenation. And when the equivalence class of every letter or every element has an inverse, the monoid is a group. And so this is one way to obtain a group from a rewriting system. So let's do some quizzes. I really am teaching my first year class now. So this is to see if everyone's fallen off the beginning. So that was my example before. And because I've made it so obvious that every letter has an inverse, because I just forced that. So it could be that some letter A, its inverse is some really complicated string, and we put them next to each other and they become the empty word. But in this case, I've made it as quick as possible. So what kind of group would this represent? What would be the equivalence classes of strings? Anyone? So if I have a big mixture of A's, little A's and big A's, and cancel, cancel, cancel until I just get either little A's or big A's. So I'll tell you the answer. It's a bit quiet like when I'm teaching online. You'll just get Z. So I hope that that's clear. So I have a few quizzes, so I hope you can humor me with these. The next one, if I've got a finite group, and then I take the set of letters to be all the elements of the finite group except the identity, then T will be quite complicated. Whenever I see two elements of the finite group, I can replace them by another element if G times H equals K. That's a rewriting rule. And the other one is I can replace G times H by the empty word if actually they're inverses of each other. So I started with a finite group and then I just created this abstract rewriting system where the letters are what they are and these are all the rules. So what would be the set of equivalence classes here?
So, I mean, presumably it's the group G itself, right?
Exactly. So these are supposed to be easy, these examples, but there'll be a point to these quizzes. So I have two more actually, but this last one will be able to actually learn something. Oh, there's something in the chat. The answer, yes, Susan, thank you. I'm sure you said it a long time ago. The last one here is that I have two rewriting systems over disjoint alphabets, and I suppose that they both have inverses, so they both present groups. Then what kind of group, so assume the first one is G and the second one is H, presents G and H. So what kind of group would I get if I just stuck the two rewriting systems next to it together? So you can do operations within the first group, but then if you have a string from the second group, then there's no interaction there. And so you can alternate between first, second, first, second.
And hopefully the free product, right?
The free product, actually. Excellent. So you get a free product from that rewriting system. So the conclusion here, which I think I have on a slide coming up, from these pretty trivial exercises now that you know what the definition is, hopefully. The conclusion is that if you have some finite groups and then you have some Yeah, we've got Z. Z was our first example, right? That you can get the integers. And our second example was finite groups. And our third thing was that you can do free products. So every plane group, because that's a plane group, is presented by a rewriting system that's obtained by just gluing together the individual rewriting systems. And we have a few extra special properties that all of the rewriting rules are length reducing. So this is 2 goes to 1, 2 goes to 0, 2 goes to 0. So they're length reducing and a few other nice properties as well. Okay, so that's the point of those quizzes. And then I have this one advanced one for anyone that wants to take a screenshot and think about it. It's a bit more complicated with A, B, and C. I've been very lazy here and thrown in the inverses straight away rather than making it tricky. And then I've got this collection of relations here. And so this is not the situation where the A, B, and C are in separate disjoint places. So I'm not claiming that this one is an easy one. I'll leave that in case someone wants to come back. So here are the adjectives. A rewriting system is finite if they're finite, length reducing if the left-hand side is always greater than right-hand side, terminating if there's no infinite sequences of factor replacements from left to right. And when you're length reducing, terminating is very easy. We're confluent if you've got W going to 2 different words, maybe after several steps. Then these 2 words have to join up later on. And that's called confluent. And if we look back at the quizzes, those examples are all confluent because in the finite group case, you're just going to zoom down into an individual group element. And in the Z example, you're just going to always get rid of the 2 types of letters and just 1 type of letter. And so it's convergent if it's terminating and confluent. And the last one is inverse closed if when you create the monoid, the set of letters is actually equal to its inverses. Okay, so you could have a group where you've got a letter whose inverse is some long word. And so inverse closed is an extra restriction that I'm going to put on. Okay, so this is a river that then splits apart up here near Sean, and then its confluence is here. So that's what confluence means. Okay. It's easier to find rivers in Australia that kind of do it a bit more naturally. So, okay. How am I going here with time? So this is a little bit more about rewriting systems. In a convergent rewriting system, rewriting any word in S star until you can't do anything else is a linear time algorithm for producing the unique irreducible word representing an element because of convergence. And if I throw one more thing in, if it's a convergent length reducing system, then at the end, you're going to get a unique geodesic word representing the elements. Okay. So here are the quiz results combining together. So if you've got a bunch of rewriting systems, then combining them with disjoint alphabets, you get a free product. And then the corollary of this, because we know about Z and finite groups, is that G is a plane group, then G admits presentation by finite convergent length reducing rewriting system, because the convergence and length reducing is preserved when we do the free products. So therefore, if I want to tell you about a plane group, it would suffice to give you a finite convergent length reducing rewriting system. Is that true? Yeah, if I say, I promise that this is a plane group and here is a finite convergent length reducing rewriting system for it. Okay, because notice it's not an if and only if statement here. It's just a one way. So now that hits upon the following, I've got it as a challenge. First of all, prove a complete algebraic characterization of groups presented by length reducing rewriting systems. And more specifically, a conjecture is that you admit presentation by a finite convergent length reducing rewriting system if and only if the group is plane. So what I stumbled on the previous slide, the conjecture is that they're the only kinds of groups that you can get from finite convergent length reducing rewriting systems. So around the same time as this conjecture, Volker-Diekert proved that if you admit finite convergent length reducing rewriting system presentation, then you're in the class of virtually free. And the proof is that he describes the context-free grammar for the word problem from the rewriting system. So we know that the conjecture is almost there already because we're at least in a virtually free group. What we need to show is that you're plane. So if we look at Basset theory, the graph of groups shouldn't have any non-trivial edge labels, edge stabilizers. Okay, and you can prove using something about the centralizer that an example like this, which is obviously virtually free, is not presented by a finite convergent length reducing rewriting system. So I have a statement coming up about how to see that. Okay, so now let me say what we've been doing lately. So Adam Piggott and I wanted to prove, or just Adam really wanted to prove this conjecture actually for a long time. But we're geometric group theorists. So why do we think we would have anything to say about all this rewriting stuff? Well, let's put some geometry or some geometric group theory into this. So here's a plane group presentation example. And if we look at a geodesic from here to here, there's a unique path. It's a unique geodesic. And from the statement that I had before, that the rewriting system of a length reducing convergent rewriting system gives you an algorithm to reduce something to the unique geodesic representative. So that's what I have in this lemma, that if you're a finite convergent length reducing rewriting system and your inverse closed is another thing that we need, then the undirected Cayley graph, where you just forget about arrows on the edges, is what's called geodetic. So we use undirected Cayley graph because the definition of geodetic graphs is for undirected graphs. So a graph is geodetic if there's a unique geodesic between any two vertices. And classifying or understanding geodetic graphs in general is an extremely interesting and I think difficult problem in graph theory. So obviously we have trees are geodetic, and then we have these things where instead of a vertex, you've got a triangle. That's geodetic. And so what other kinds of geodetic graphs are there? It's a good question. So that's the first thing, that the Cayley graphs are actually these graphs with unique geodesics, which is an interesting property. So here's another one. So if G is presented by a finite convergent length reducing rewriting system, which is inverse closed, and U is one geodesic, and V is another geodesic, and they end an edge apart, and they only have their start vertex in common, and they branch out straight away. So it's not finished yet. There's space there. At the moment, there's no, probably should be a comma. So if we're in this situation and you're a finite convergent length reducing rewriting system, so these two are geodesics. So there's no rewriting that I could do on there. So the only place that I can do rewriting, so U followed by this edge, it's a bit like automatic groups. U followed by that edge is not reduced. So therefore there has to be a rewriting rule somewhere. But as soon as I do a length reducing rewriting rule, it's going to drop down length at least 1. And so I'll be straight away onto V. So the conclusion is that a bit more, that U and V are the same length, and they're at most the maximum length of a rewriting rule left-hand side. So because you have to drop down straight away, you're actually going to drop down to the beginning of the word there. So that means that this is less than or equal to the maximum length of a right-hand side. So this observation was actually in Andrew Everly Price's master's thesis from Melbourne Uni when he's studying geodesics in Untitled Graphs. So it's a nice observation, and I gave you the proof, a bit hand waving. And so we call this broom-like, that you have a really long geodesic followed by a thing, by an edge, then it just branches off just at the very end, like that. So obviously in the picture of PSL2Z, this is exactly what we're going to see, that if you branch off, then it only happens at the very triangle. And so this is a property of all Geodetic graphs of finite convergent length reducing rewriting system. So we know that they're virtually free and hyperbolic. So we're expecting triangles to be behaving like hyperbolic triangles, but it's a bit more extreme than that because it jumps, it's bounded by RT. So here's another geometric consequence that is now our geometric characterization of, so this is the less easy statement. So definition, a group has the K-bounded non-degenerate triangle property, where K is an integer, if each side of any non-degenerate geodesic triangle, so a degenerate geodesic triangle is when you have a geodesic and then it follows on itself and then splits off, and then maybe it does that. So that would be degenerate. So a non-degenerate one is when you branch off straight away, that there's no connections there. So a group, I guess a group, or with respect to a finite generating set, has this property if every non-degenerate geodesic triangle in the Cayley graph, undirected Cayley graph maybe, has length, side length at most K. In a while to spit all that out. So that's a property. So it's stronger than being hyperbolic, because you can have very long geodesic, they just stay very close together. So this is a much stronger property than being hyperbolic. PSL is the only example that I'm giving you. And this one definitely has the bounded where K equals 1. So theorem A is that if you've got an inverse closed finite generating set for the group, then G admits a presentation by an inverse closed finite convergent length reducing rewriting system over those generators with the maximum side length of a right-hand side less than K, if and only if the Cayley graph is geodetic, which we already have, that one direction, and has the K-bounded non-degenerate triangle property. So this is characterizing which groups are presented. So unfortunately, this doesn't immediately say it's plane, but we think it's a pretty interesting geometric restriction to have on Cayley graphs. Okay. So that's that. So that was our first observation, that we can characterize triangles like that. And so what can we do with this? So here's a few statements. So Madeline and Otto, back when they were making the conjectures, have this statement about centralizers, that if you've got an element of infinite order in a group presented by finite convergent length reducing writing system, I think I'm back to sigma. Normally I call this S. I'll tell you why at the end. Then the centralizer of an infinite order element is actually isomorphic to Z. But using theorem A, we could actually beef this up a little bit. And then I think this should say inverse closed. There's a few little typos on this slide because we're using theorem A, and that's only about inverse closed systems. And you've got two non-trivial elements that are conjugate. Then G has infinite order if and only if that. We already have that from Madeline and Otto. If and only if, so G has the centralized has infinite order if and only if the set of conjugating elements has infinite order. So if G has finite order, then the set of conjugating elements is finite. And that's something that we're going to use. So let me give two more statements, and I think I've got these a little out of order. Another consequence is that if you're presented by one of these rewriting systems, then every finite subgroup in the group is conjugate to one that lives inside the ball. So we've got a finite subgroup H, and then it conjugates to something that lives inside the ball of radius RT, this maximum side. So we're starting to be able to understand what the finite subgroups are doing in these groups. What we'd like is that they're all just free product of these finite subgroups. So here's the statement that allows us to prove that the set of conjugating elements of two conjugate elements, the set of T's that do the conjugation, as we see here, is finite. So it's even stronger than this. It says, well, it's equivalent, but if you're in one of these systems and you've got two non-trivial elements that are conjugate and they're both of finite order, and T is a conjugating element, then the length of T is actually bounded by this amount. So the G and H are in the ball of radius K. So we can draw G like that and H like that. And now they're conjugate. So T is we'll choose a geodesic for T. Let me imagine for a moment I'm just in hyperbolic space. Then the picture would look like that, which we've all seen when we've done hyperbolic groups and rhomatic groups and things. But now we're in light of theorem A, we're in a geodetic Cayley graph where triangles, non-degenerate triangles, have to be just bounded by size RT. So the picture doesn't look like this. It actually looks like this from the paper. So that T is not allowed to, it can only live at most RT. So this is a very sketchy thing, but this is one of our significant points, that the length of the conjugating element is actually just bounded by this. So this is the same T top and bottom, and this is branching here, so it has to be a different letter here. So just by some combinatorics on words that we get a contradiction that this W can't be very long. So it's quite a nice proof. So these are all these, let's say, random facts that we get from knowing about bounded size non-degenerate triangles. So now let's put it all together. We have one more statement, and this is again coming from Basset theory. But the statement's quite easy. We define a relation twiddle on the set of tilde on the set of non-trivial finite order elements by A is related to B if the product has finite order. So A and B are finite order, and if you put them next to each other, they still have finite order. So in a plane group, in a free product of finite groups, if you take one group element from here and one group element from here, their product is going to be infinite order by normal form theorem. And if you take two in the same factor, then they'll have finite order. So this relation is, in plane groups, this relation is transitive. So if you have this is related to this and this is related to this, then they all have to live in the same subgroup. So it follows easily from normal form theorem of free products that in any plane group, this is transitive. Theorem B is our algebraic characterization, and it says that if a group is plane, any non-trivial finite order element is contained in a unique maximal finite subgroup, and each subgroup is conjugate to one that lives inside the ball of radius r, is a statement I had before. So we can track it down. And then the third thing that's critical is that the relation is transitive on the set of finite order elements in G. So it's an if and only if with plane in one of these systems. And the fourth point is that the relation is transitive on the set of elements of geodesic length at most this quantity 11 RT. So I can tell you a little of how the proof works there, although my time is running out, so I can't. That it's just all about what I said, that every finite order element is living in a unique maximal finite subgroup. That subgroup is conjugate to one in a ball of radius RT. And we know that the length of a conjugating element between two finite order elements is bounded. So we can make all the action happen inside this ball of 11 RT. So what this tells us algorithmically is that if you wanted, oh yeah.
You don't assume here that the alphabet of the Writing system is closed under inversion.
Inverse close is hidden.
Okay, it's hidden. Okay,
it's
thank
hidden
you.
in the in the horrible acronym that we have.
I see. Thank you.
Yeah. So definitely we're only restricted to that because of our geometry observations. And so what this tells us algorithmically is that you can check finitely many elements. You can create the ball of radius n. We need to know how to tell whether something's finite order. And then we only have to check that finite, come on, it's just a ball, so it's got exponential size, not too big. Check all those things for transitivity. And if it fails transitivity, what's actually going on there is that it's amalgamated free product over a non-trivial group. And if it is transitive everywhere, then we're guaranteed that the group is plane and we can solve the conjecture. So that's number B. Theorem B just says we need to check whether or not it's transitive on a finite set of elements. And Narendra and Otto, 88. So we're always calling back on these old results. Given a polynomial time algorithm to decide whether an element is finite order I don't think you need the inverse close for this because it's the old school things. So we've got everything in front of us. So using these facts, this is one way to express what we have. The following problem is in NP. So on input, inverse closed, finite convergent length reducing writing system, is the group not plane? So that I can do NP. So if it's not plane, I simply have to produce a certificate of 3 finite order elements. You can check that they're finite order in polynomial time, and you can check transitivity as well in polynomial time. So you can verify that it's not plane by finding a counterexample to the conjecture, by finding those 3 elements. So that's our theorem. And I want to finish with the isomorphism in 5 minutes. So my student, John Koo, I put a picture at the beginning, has coded all this up in Python and tried to run it, but obviously the size of balls is still pretty big. So we're going to be breaking some supercomputers at UTS to try and get this to give us anything interesting. But yeah, everything is quite programmable. So my last 5 minutes, so that's the results of the geometry and then the algebra. And so my last 5 minutes, I want to talk about the work with Yuming, Heiko, and Armin. Yuming and Heiko are finite group theorists, experts in finite group isomorphism algorithms. And so we brought them on side because we have a whole bunch of finite groups sitting inside our plane groups. And so we needed to know things. So recall the discussion, I'll do this very quickly. Isomorphism, just given two abstract presentations, undecidable, with a promise that they're in some class, it's decidable, but no complexity bounds possible. And for virtually free groups, we could have a context-free grammar or a virtually free presentation, and we'll get some space complexity. Okay, so my result at the end is about a complexity class between P and P space, or between NP and P space, I guess. A language is in sigma KP. There's a bit too many P. I should call the predicate Q. If there is a polynomial P and a predicate Q that can be evaluated in polynomial time, so here's the predicate at the end, you have to just put these inputs W, X, Y, Z into the predicate and decide whether it's true or false. Such that a word is in the language if and only if there's a binary string of polynomial length. There exists a binary string of polynomial length such that for all binary strings of some length, there exists another binary string, and then you alternate for all there exist. And eventually you stop, and then you say, you stop after K steps, and then you have to evaluate this predicate. So there should be a ... there. I was thinking about sigma 3. So sounds a bit obscure, but NP, I don't know if this is on the next slide, NP is equal to sigma 1P, because one way to express NP, which I already have used, is that something is in the language, say a Hamilton path or something. So some particular graph is in the class of Hamiltonian paths, if and only if you can find a certificate X1, and then you don't need any of these other things. And the predicate is simply given the graph and given this certificate, which would be a path in the Hamiltonian case, you can verify whether that path is Hamiltonian. So NP is equal to sigma 1P, and then sigma 2 and sigma 3, etc., are just a hierarchy of things which potentially could all collapse. Yeah, so here we have the hierarchy, and all of these things can be done on a Turing machine in polynomial space, because you can write all these things down, your guesses, and then you can run through all X2s, then you can make another guess, X3, and then you can run through all X4s, and you can do all of that in polynomial space. Okay, it may be a bit much for the very last few minutes of a talk, but it's a pretty interesting area. So L belongs to sigma 3P is the class that we actually have in our theorem. There's the statement of that one. It's a bit easier to read. If there exists an X, Y, Z, yeah, that's where I got the thing. Yeah, I should call this Q so it's not confused. The P here stands for polynomial. So apologies for that. So that's that class. And here's the theorem. And this is with the guys there. So the following problem is in sigma 3P. On input, two plane groups presented as inverse closed finite convergent length reducing rewriting systems. Is G isomorphic to H? And so that's our analog of Senejas and Wise's results. And we claim that the input being inverse closed finite convergent, whether or not the conjecture is true that the plane groups are exactly the groups presented by those things, is immaterial here, because we know every plane group does have a presentation by one of those. So our algorithm takes this presentation to rewriting systems with the promise that they really do present plane groups. And obviously we can verify anyway, whether or not they're plane using theorem C. So the proof, you've already seen glimpses of this, that we know where finite, we know that there's every finite order element lives in a maximal finite subgroup, which is conjugate to one that lives inside the ball of radius RT. So we can identify finite subgroups, and we can, what we essentially do is we guess, in the first step, we guess generators for each factor of our plane group. And then we run through for all. So this is running through a ball of some radius, which is polynomial size. And then we need one more thing, and these are actually going to be straight line programs when you get into the proof. And so we're actually using results of Babai on sizes of generating sets of finite groups and isomorphism of finite groups. So it's pretty cool, and I'm out of time to give you all the details, but that paper is going to appear in Stacks next month. So you'll be able to find it. So yeah, I think I'm out of time. So I have the Babai stuff, and I'll say thanks.
All right, thank you very much. Thank you, Murray. Okay, so if there are any questions to Murray, so you're welcome to ask them now.
I'm just curious about going back to the inverse close thing. I understand you needed that for your geometry, but you know, there's a difference between not breaking it just a little bit and assuming and insisting, for example, that the inverse of every generator be a word of at length at most 2 in the generators or something. Is there a way to fudge that a little bit and get things to still work?
Yeah, that's a really good point. We should look into that. For now, we're just restricting to the inverse close because it's easy, but eventually we're going to have to cross that bridge. Yeah. Yeah, that's a good point, that if they were bounded by a finite number, then we might still be able to make a geometric statement. Yeah.
I mean, I guess it's always going to be bounded by a finite number because there's a finite number of generators in the first place, but I'm just kind of wondering.
Yeah.
If the number 2, I don't know.
Is helpful.
Anyway.
Yeah. Yeah, I mean, that you know, Adam's work on Gilman conjecture, that was where all the drama is when it's not inverse closed. So, yeah.
Could you show what was on the very last slide that you skipped?
Sure. So I was way too ambitious with all this stuff.
In fact, you had more time. You see, you had 60 minutes. You could have.
I could have gone all the way to the end. Yeah, so you can have these slides on my webpage as well, I should have said. So you can have a look at all the things I went too fast at. This is the sketch of the proof, so I don't know how helpful this is going to be, but you've got 2 rewriting systems presenting 2 groups. So this is something we just do in our heads. We guess that the plane groups look like these, the same rank free group at the end, and then the same number of finite factors. So the X, Y, and Z are part of the sigma 3p definition. And so the first thing we do is guess generating sets. And Babai, an old result of Babai is that every finite group has a generating set of size log the size of the group. It's a very easy one. And so these will be polynomial size. And then, so we're guessing generating sets actually of the same size because they're going to be the same groups. And if our guesses are wrong, then sigma 3 just says that's fine. Then, you know, you're only supposed to be verifying that they're isomorphic. So we guess the generating sets, and then we let Y run through the ball of these radius. Actually, we improved the +2 to just RT now. So we run through the ball of radius RT, and that's going to contain all the finite order elements that we need to look at, because every finite order element is conjugate to one in the ball of radius RT. So we run through all of these and we check that every finite order element lives in exactly one of these finite groups. So how do we check that? We then guess a straight line program. So this is how it goes. There exists the X, so we're stuck with that. Then we do for Y, so we choose one at a time, an element of finite order. And then for each one of those, there exists a straight line program, which again is from Babai. Babai guarantees that the length of the straight line program, which tells you how to express the element Y in terms of the generating sets. So hopefully this is not too complicated. And so that's of polynomial size, that Z, that's what we're having to worry about. And then we also need to guess conjugating elements, which turn out to have that length. So there's quite a lot going on, but the ideas are all here. And so once we do that, then the predicate P checks the free product decomposition using theorem B. So it checks that maximal finite subgroups are all where they're supposed to be. And then we've got generating sets for finite groups, AI and BI, and Babai and that name have an algorithm with straight line programs that tell us how to check isomorphism for finite groups. And then finally, the easiest bit actually is to figure out the rank of the free factor using Smith normal form from linear algebra. You just take the abelianization of the groups and you can work out the R. So that's what's happening there. So originally Adam and I just had a P-space algorithm, which was kind of doing these steps, but in a much more straightforward way. But Armin actually pointed out to us that, you know, you could use Babai's results to do things really efficiently with straight line programs and things. So yeah, that's the proof of, and before this project, I'd not really known what sigma 3p was, or sigma 2p. So now I know what it is, that you guess, run through all, and then guess, and you go as far as you need. And Susan probably is familiar with rewriting systems always using sigma, but we had to get rid of sigma because that's the name of the complexity class.
Okay. It would be cool, Murray, to have this problem complete in sigma 3p.
Yeah, absolutely. But I don't know what you could use to reduce or anything. Yeah, we need to shave off this and make it sigma 2p. And so we had a few ideas about how to do that, but I wouldn't put money either way.
So it could be in sigma 2, right?
Could be in sigma 2.
Okay.
We couldn't figure out how to do a couple of things. Yeah. And the whole hierarchy could collapse, but yeah, I wouldn't think that ours is the most optimal thing. It's just it works.
All right, very good. Are there any other questions or comments?
I have a question. Let's consider some simple example. For example, let's consider the free product of two groups of order 6 amalgamated it's a group of order 2. Okay. Yes. Okay. So it looks like it's difficult. It's a difficult question to find out if it has not rewriting system which is convergent, finite, and length reducing. So it looks like a difficult question. So is it correct?
We're working on this one, this exact example right now. that if these were two cyclic groups, then the centralizer result tells us that it can't be possible. But we don't have anything other than that centralized result. So this is our minimal example, minimal criminal, I think.
So it's not known anyway.
We don't know this one, but we've got some ideas about how to rule it out. But yeah, that's a very good. You've spot on with that, and the transitivity is exactly picking up, you know, whether you've got something that's in the middle of two groups of finite order. Yeah. Yeah, can we prove every generating set has a Cayley graph where the triangles are not? Yeah, I don't know how one will do that.
Exactly.
Yeah.
To have finiteness of rewriting systems, that's a very restrictive condition, of course.
Yes.
But if, for example, you have infinite, but not really infinite, sort of narrow, it's growing, say, polynomially, or then efficacy would be similar because it's fast. If few relations of given lengths on the left-hand side, you can apply them quickly. That probably would give you a lot of groups.
Mm. Yeah.
Do you know which?
Quite a lot of groups which are given by Stallings pregroups, universal groups of Stallings pregroups. They have this type of length reducing infinite systems, convergent, of course.
You're talking about the entire word problem?
Entire what?
You're talking about the word problem, right?
Yes, to get to the reduced element, because it's convergent, there is a normal form. So it's infinite, but it's convergent. It's you can quickly get to compute the reduced form. It's still efficient. Not linear time, because you should go
search. Yeah.
But many groups, like not only free products of Z and finite groups, say, it's universal groups of Stallings pregroups. I'm not sure the growth of rewriting systems, but they have infinite convergent length reducing rewriting systems.
Oh, I see. So that's actually about normal forms. Okay.
Mm. That's in your paper with Andrew Duncan and Volker that we've read many times. But
we did not do it was just a result about that exists. But if the growth rewriting system is if it's narrow, sort of few relations of a given left-hand side length, polynomially many, then it's very efficient machinery to compute normal forms. And many more groups.
Okay.
Anyway, interesting talk. So, Murray, you think it's their conjecture is true?
Well, what I really want to be true is that this computer program we're writing churns away at random and just stumbles upon a length reducing writing system where the transitivity fails. That's my dream.
Yeah.
Yeah. And we can identify, you know, the finite factors and things like that as well. So, yeah. But I think Adam is pretty convinced that it's true, but I want the computer program to
find a counterexample.
Find a counterexample. Yeah.
That would be more interesting.
That would be fantastic, actually.
Yeah, but of course, with computer programs, they usually deal with some sort of random examples, and the random examples.
Yeah, will be boring. Yeah.
I mean, for various reasons, which we cannot quite explain, they tend to satisfy all of these conjectures.
Yeah.
Okay. Any other comments or questions? So one general comment that I wanted to make is that although Paul Schup's name was not mentioned in his talk, I think that as far as I can tell, a lot of what Murray was talking about was in fact sort of informed by Paul Schup's work, because of course the Mahler-Schup theorem seems to have been pretty much
absolutely, and we've been
and
looking
also,
at
and also the name of Harry Smith, whom you mentioned, right? His theorem of plane groups. I believe he was a student of Schup, right?
I think so. Yeah, I think so.
Yeah, and I think Paul would have really liked this talk.
Okay.
It's
yeah, we've been having Linden and Schup open a lot of the time. We looked at one related groups and things. So yeah, definitely.
All right, very good. Okay, thank you. Let us thank Murray once again.
Thanks, everyone.
Okay.